All right, hello everyone. Welcome back to Physical Geology 1403. How we doing? You made it through day one. Congratulations. 15 more to go? Right? Yeah, you got this. It's not that bad. What do y'all think? Is my class going to be the hardest one you take this semester? No? Oh, I hear some very confident no's. I like that. What else are you taking? English? You think English is harder than my class? Wow! English composition. Who are you taking it from? I'll tell Sam that you said that. Okay, great. Yeah, I won't tell him who said it. Okay. Who thinks that this is going to be your hardest class this semester? You might be right, but I promise that it is achievable. I promise that you can do it. Here are some tips, okay? Always ask questions. I'm going to bring that up like every time, right? Get used to it. Always ask your questions, and you can get tutoring. Now, tutoring is an option two ways. You can get tutoring from me during normal business hours, assuming I don't have any other previous assignments or meetings that I have to take care of, okay? I am happy to tutor you individually or in groups right here in this classroom. Or if you're one of my online students, we'll do it over Zoom or we'll do it over Blackboard class, okay? But I don't know that you need tutoring unless you ask me, all right? The other option is if you can't do tutoring, this is most common for my online students, during normal business hours because you work a job or something like that, or maybe you're in other high school classes throughout the rest of the day and you can't take time out of your day to do that, there is a tutor at the LRC. Her name is Sue, and she is specifically for geology students, okay? I have her information posted on my the window of my office, for those of you that are here in person. I think I have it in the syllabus as well. If not, I'll double check that when we're out of class today. Let me just write a little note to myself, and I will send out an email to everyone with Sue's information so you can set that up with her. But what you would do is you would go through the LRC, you would set up a normal tutoring appointment through the LRC, and you would just select geology as the subject, and it'll automatically book you with Sue, okay? But I can send out a reminder of that. Send Sue info, okay? I can do that after class today. So if you're already feeling a little lost or dismayed or overwhelmed, please don't. It's far too early to feel that yet, okay? You barely even learned anything. Give me a chance, right? Give me an opportunity to blow your minds before you make up your own minds, all right? Okay. Before we start every class, I'm always going to give you the opportunity to ask questions. Anything that you have chewed over since the last time we met, anything that's come up in the world that's made you want to ask a question, it doesn't even have to be geology related, right? Anything you guys want to talk about or ask? No? All right, well, I'll give you one fascinating little snippet. My astronomy majors might find this interesting. There is an asteroid that was titled 2024 YR4. You've been following that at all? No? It's about a 200-foot long asteroid. Yeah, with for the last couple of years we've been tracking it. Small chance that it was going to hit Earth, but the most recent calculations that were just published not long ago have found that it in fact won't hit Earth, but there's about a 5% chance that it'll hit the moon. Which, yeah, that would be some cool fireworks to watch through a telescope, right? A 200-foot asteroid hitting the moon. It'll melt rock. It'll make a plume of debris. It'll be pretty cool. It won't change the orbit of the moon or anything. It's not massive enough to do that, but it would be a cool thing to watch. The first time that we can actually record something that big hitting our moon and have footage of it for education and learning and all of that. I'm excited. I kind of hope it does hit the moon because that would be awesome, right? We'll see. It's only a 5% chance now. But yeah, a little fun factoid for you. All right, so last time I gave you a brief overview and introduction to geology. Okay, today we're diving deeper onto the subject. Okay, we're going from the macro view, the large viewpoint, the global perspective, and we're zeroing in on the smaller minutia. Okay? What makes the stuff that we see? We're going from that Earth as a whole to what makes Earth. All the tiny little components, okay? Like a blade of grass as compared to the rest of the planet, except even smaller than a blade of grass. Because we're talking about matter. What is matter? Well, nothing. What's the matter with you? Right? That's the proper answer if I ever ask that. No. All right. What is matter, though? I need someone to be my ba-dum-tsh guy this semester. All right? All right. What is matter? What everything is made out of? Sure. Yeah. Anyone else want to offer another explanation?
Isn't it solid, liquid, and gas?
Solid, liquid, and gas are states of matter that we are absolutely going to be diving into today. But matter itself, other terms, other things that are put together. Well, yeah, so everything is made out of matter, right? Me, you, this table, this remote, all of it is made out of matter. Everything that you can see and interact with is made out of matter. The air is made out of matter. Yes? Atoms. Yes. Okay. Atoms. So when we say matter, what we're actually referring to are the tiny particles that make stuff. Stuff is a weird word when you think about it, right? I'm not duolingual, but I've been told that there is not another word in another language that's quite like stuff in English. You can stuff stuff in English. And all of those stuff have, those words of stuff have different meanings in that sentence, right? It's a weird word, but it's what makes all the stuff around us, okay? So we're looking at atoms, and there are three particles that make an atom. Your protons, your neutrons, and your electrons. Your protons and your neutrons together make a nucleus. That's the center of your atomic body. Then you've got your electrons that form an electron cloud or orbit around your nucleus. Depending on the atom in question, you will have different amounts of protons or neutrons and electrons in that atom. Now I want to clear up a little thing that most people seem to have a misconception about, okay? An electron orbit is not like a planetary orbit. It doesn't follow the same path around the atom over and over and over, okay? Electrons are not doing this. Okay, here we have our nucleus, protons and neutrons. The electrons are just following the same linear path all the way around and around and around and around in the same order over and over and over. That's how most people perceive electron movement. That's not actually what it is. I used a term earlier when I was talking about electrons. I said electron cloud. Think of electrons more of this. Tiny particles, about 1/2000th the size of a proton, by the way, okay, that are zipping around the nucleus so fast that they make a hard shell around that nucleus. And depending on your atom, there are multiple shells, okay, multiple layers of electron shells. That's what gives things substance. The electron shells of the atoms that make my body are interacting with the electron shells of the stuff that makes this table, giving it that tangibility, that interaction. The two objects are bouncing off each other because of the hard exterior shells of the atoms that make up both. Okay, so this is how an atom is built. Okay, these electrons are traveling 1,360 miles a second, and that is so fast that it's essentially a hard barrier around that nucleus. So how do we differentiate our atoms from each other? Well, yes, they've got variations in electrons and variations in their nucleus. Let's talk about each one of those things. I'm giving you a baseline for chemistry right now. There's also going to be a little bit of basic information I give you about physics. But I don't dive too deep into either. I'm just going to give you enough of a refresher that hopefully whatever physics and chemistry you've taken already, you'll start to recall it. For some of you, it might not have been too long ago. For some of you, it might have been a year or more. But hopefully you start to recall it so that the things that come later will make more sense. Okay? Okay, we have 94 natural and 24 synthesized elements. What does synthesized mean? Man-made. AKA, does not occur in nature. Why do we have them on the periodic table? Because for even just the slightest moment, and when I say slightest moment, I mean like a picosecond, they existed. And the mere fact of their existence deserves them a place on the periodic table of elements, at least in our estimation. We're the ones that constructed the table, so we get to decide what's on it, right? So, and by the way, this is something that's constantly changing. We actually we develop a new synthesized element at a rate of about 1 or 2 every decade, okay? This is just the most recent one. Actually, the textbook that I used in this class before I eliminated that textbook 2 years ago to make my class completely OER said that there were only 20 synthesized, and it was written in the 2010s. So I eliminated that book, and as a process, updated my slides and did everything like that. We have 24 synthesized now. All right. Okay. So let's talk about our nucleus for a second. The nucleus of all atoms is made out of what 2 particles again? Protons and neutrons. Good. Protons have a net positive electric charge. Electrons have a net negative electric charge. What charge do you suppose neutrons have? Neutral. They don't have any charge. Bear that in mind. Now there's this thing on this periodic table. I'm going to emphasize this large kind of blown up one right here. Hopefully the camera can view me on this. There are a few designations, a few names, a few numbers that we've got on each one of these elements on our periodic table. We've got the actual name up here. We've got this number here. We have a symbol here. And then we have another number here. We're going to focus on these 2 numbers right now. Okay? This number, 19, we call that the atomic number. Do you know what dictates the atomic number? Huh? The number of what? The number of protons. What did you say over there? The number it was made? No. No. So I think I see what are you referring back to the R process from last time? Yeah. Okay. So that actually is not why we put them in this order. It's just that's kind of the process they were made in. So what he's talking about is the R process we discussed last time in the nebular theory of how star systems are made, right? The first stars formed out of hydrogen. They cracked apart those hydrogens. They used fission and fusion processes to build the next element, helium, and then after that, lithium, and then after that, beryllium, and so on and so forth. So you're right, it does follow this progression of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth in our periodic table, but that's only because every time you rip apart an element, the larger and more particles it contains, the more energy it erupts, right? It creates, and therefore you can make newer, larger particles, right? That's the natural progression. We actually have them in this order because of the same reason, but not through the R process, okay? It's not because of the R process we put them in this order, but both systems align to the same common factor, which is the number of protons in their nuclei, okay? So there is 1 proton in hydrogen, which is why it is up there as number 1. How many protons does helium have? 2. Lithium? 3. Sulfur? Oh, I gotcha. No, sulfur does not have 4. Yeah, there we go. Gotcha. All right. Okay, so the number of protons in the nucleus determines what the atomic number is. So that's the first property. Okay? Now, there's the other number. Before I move on, I'll just mention this other number is called the atomic mass. Okay? Now the mass is the total amount of, well, mass that element contains. I'm using the word mass as opposed to weight. You may hear the term atomic weight. That is actually incorrect. We call them atomic mass. What's the difference between mass and weight? Love the necklace, by the way. That's cool. Is that an ammonite?
No, it's just a black scorpion and acrylic.
Oh, nice. Cool. All right. What's the difference between mass and weight? Speak up. Say it louder so everyone can hear you. Don't be shy. We're going to be together for 8 weeks.
Weight is how much something weighs, and mass is how much something takes up space.
Taking up space is more of a volume, which includes mass as part of the equation. Well, mass and volume together make density, okay? You didn't quite give me the whole explanation there, okay? I feel like you've got the concept. You just have to give it to me in the proper terminologies. Anyone want to help her out? Remind me what your name was again?
Chris.
Huh? Chris, that's right, Chris. Anyone want to help out Chris? The difference between mass and weight. I'll give you one of the definitions. Which one do you want? I'll give you mass, and then you guys explain weight to me from there, okay? Mass is the total amount of matter, atoms, particles, within a given substance. So, then what is weight? Because that sounds a lot like weight, but weight includes one other factor. Bingo! Weight is dependent on gravity. Gravity, that force in the universe that is caused by the presence of mass. Each of you, are probably aware of approximately how much you weigh at this given time. We increase our mass by, say, having lunch, adding matter to our bodies. We gain a few pounds after lunch. We don't eat for a day. We lose a few pounds. That is mass. Weight is determined by the factor of gravity that we have here on Earth. If I were to all of a sudden just snap my fingers and go to the moon right now, would my mass change? No. I have done nothing to remove or add mass to my body. What has changed? My location on another place that has more or less gravity. The moon has way less gravity, right? So I'd be able to jump 10 feet in the air. There are videos of astronauts doing just that. Why? Because while their mass is consistent, the gravity quotient has changed, and therefore their weight is far less. So, this is a concept that comes back up later, by the way. Atomic mass, not atomic weight. Because mass we can measure anywhere else in the universe. Weight is dependent upon your location to a source of gravity. Okay? I can go out to deep space and still measure mass. Weight is irrelevant out there. Okay, so let's talk about the ways that these elements come together. We call these bonds. Okay, and there are several different kinds of bonds. Bonds are caused by, often, heat and pressure. Those are the two factors that most commonly influence the presence of bonds. The formation of bonds, also the breaking of bonds. Easy example. Gavin, what's your favorite candy bar? Snickers. Ooh, that's a good one. Good choice. What happens if Gavin leaves his Snicker on his dashboard today? It's going to melt. Why? The heat. What's that heat doing? It's adding energy, and that energy is disassociating certain bonds in the chocolate, the nougat, everything else that you got in there, okay? His Snickers bar is going to melt, and it's going to be a mushy mess by the time he gets back to his car and hits his forehead for leaving it in there, right? Go back home and throw it in the freezer. Enjoy it tonight, right? But what happened there? The bonds broke apart inside of his material. Now, on the smaller scale, bonds can form and break between individual atoms as well. So the different bonds that form, we've got ionic bonds, covalent bonds, and metallic bonds. Now, as a rule, most elements like bonding with other stuff. There are a few exceptions. I'll get to that in a minute. But atoms in general like to be more stable by being bonded to other atoms. Stability is a big factor in the natural world. Okay? Stability is important. Doing okay? Okay. All right, stability. In general, things in nature are seeking a state of stability. Okay? Remember that. It's going to keep coming up. So let's talk about why we get these bonds and why they tend to be more stable. There is this thing called the octet rule. Has anyone heard of this? You're nodding your head. Jackson. You don't remember? That's okay. I give you the definition on the board. Atoms tend to gain, lose, or share electrons until they have 8 electrons in their valence shell. Oh, but what is a valence shell?
It's the outer shell.
The outer shell. Bingo. Why the outer shell? Huh? Are any of the inner electron shells of my atoms interacting with the inner electron shells of this table? No, the outer shells are what interact with other things. And so, yes, 8 electrons in the outer shell, that's the octet rule. Atoms tend to gain, lose, or share until they have 8 electrons in the outer shell. Why 8? Rule of the universe. Who knows? We don't know. It just is. I'm sure there are tons of quantum physics professors discussing the philosophy of that. But in the end, it can only come down to one answer: because. It's just the math of the universe. We often try to explore why, and I love trying to explore the why of the universe. It's what drives me through a lot of what I do, is trying to understand the why of things. But in the end, a lot of these things come down to it just is, no matter how much time we put into trying to figure out the why. So 8, that's where we're at, the octet rule. And they will make bonds to satisfy that rule. In the case of ionic bonds, electrons are transferred from one atom to the other. In the case of covalent bonds, electrons are shared between the two or more. And in the case of metallic bonds, all of the outer electrons are shared within all of the same atoms in that given mass. Okay? So let's talk about each one of these examples. An ionic bond. This is what happens when elements or atoms that we refer to as ions bond to each other. An ion is an atom that has an electric charge. There are 2 electric charges. What are they?
Positive and negative.
Positive and negative. Thank you. Now, which one of the 3 particles that we talked about that make an atom have a negative charge?
Electron.
The electrons. Which one has a positive? Protons. So if I have an atom that has more electrons than protons, what's its charge going to be? Net negative. And one that has more protons than electrons? Net positive. So if I say introduce a net negative electron to, or a atom to a net negative or a net positive atom, what are they going to do?
Cancel out, it'll be neutral.
Well, not yet. What are they going to do first? If I have something that's positively charged and something that's negatively charged, what happens? What happens when I put 2 magnets near each other?
They're gonna
Zip.
attract.
Yeah, they're attracted. Opposites attract. And just like that, I saved you thousands of dollars in relationship therapy. Okay? All right. Opposites do, in fact, attract. Magnets, electrical charges, okay? They are drawn to each other. It's a rule of the universe, just like the octet rule. So let's give you an example. Sodium. Where is sodium on our periodic table of elements? Number 11. Fair enough. Let me show you a different way of looking at this table. You have been looking at the atomic numbers. You may even have been glancing at the atomic masses. Notice that they are in columns as well. The column they are in is important. Column 1, 2, we skip over these for now. 3, 4, 5, 6, 7, 8. How about that? What might these 8 columns be referencing? The number of electrons in the valence shell. Sodium is in column 1, meaning it has how many electrons in the valence shell? 1. Okay, so where is chlorine then?
7.
Yeah, which means it's in column what? 7. How many valence electrons? 7. We have an atom with 1 valence electron and an atom with 7 valence electrons. How many do each of them want?
8.
They each want 8, but they only have 8 between the two. What are they going to do? They're going to zip together, because guess what? The sodium is positively charged and the chlorine is negatively charged, right? They're going to zip together, and they're going to form a shared, or not a shared, the sodium is going to transfer its 1 electron over. So the chlorine technically is 8, but the sodium has the opportunity to be attached to that 8. So it is also satisfied. And this makes a bond that we call sodium chloride. Do you know what that is?
Salt.
Salt. Salt, sodium chloride, one of the most common bonds that you will encounter on our planet. Our ocean's full of it. Your bodies are full of it. It's in your water. We can't live without salt. We are dependent on it. Okay? Sodium chloride, very common ionic bond. Pretty easy to get. Cool? Yeah,
Can I answer a question?
you may. All right, that's ionic bonds. Any questions about ionic bonds? So an ion is a positively or negatively charged atom. Okay, remember that one. Let's talk about covalent bonds. So while an ionic bond is where an atom transfers electrons to a different one and it satisfies both of them, a covalent bond is when the electrons are actively moving between both particles, both atoms. Easiest example of this is a hydrogen gas, H2. Okay, 2 hydrogens that approach each other, and the outer electrons are equally drawn to one nucleus as they are to the other. And so all of the valence electrons kind of zip between both atoms, making H2 gas, hydrogen gas. That is a covalent bond. Now, metallic bonds, these are cool. In a metallic bond, metals are a substance that freely share electrons between all of the particles, all of the atoms in that substance. This is really, really useful and really, really important to us. Why? Most of what we have is made out of metals. We use metal a lot. What things do we have made out of metal that you think are most important in reference to this concept of electrons being shared freely? Oh, my camera lost me. Over here, kiddo. Right here. Right here.
Wiring.
What about wiring? My camera's being a little... There we go.
They conduct electricity.
Bingo! There it is! Conduction. You ever plug in your toaster and you see that blue zip, that blue zap? You'd be like, oh, I'm glad I didn't touch that. I was touching the plastic. Good for me, right? Do you know what that blue zap is? Electricity. Do you know what electricity is? Energy. Electrons. That blue zip, you're seeing trillions of electrons transferring from that metal to your toaster in 1 second, just the blink of an eye. You just witnessed a whole bunch of electrons. Those electrons are electricity. The only reason why we have electricity, right? Thank you, Thomas Edison and all of the other fathers of electricity, Nikola Tesla and all those other guys, is because of this concept that metals freely transfer electrons through their substance. So if I have a bar of metal and I put some electricity in this end and I touch that end, I'm going to get electrocuted because of this fantastic concept called conduction. Only possible because of the metallic bonds that are shared between those substances. Cool? Any questions about that? Gold, silver, and copper, the list I've got up here, the best conductors we've got. Most conductors that you'll find are made out of copper. Of these 3 options, it's the most common. Okay? It's the cheapest because it's the most common, right? Copper is more commonly found than gold and silver. I'll talk more about metals, mining, and stuff like that later on. Was there a question over here? I thought I saw a hand. Did you have a question?
I saw a video and I don't know how true it is. They took an ice tray and put vinegar in it, and the nails, they put copper wire around the nails, and one nail went into one side and the copper wire went into the next slot, and it somehow turned on a light.
By transferring through the vinegar.
Yes.
Yeah, so you can transfer electricity through liquids, through certain liquids. Water, easily.
There was no electricity unit to it though. It was just
Oh, okay. It was
copper.
it was transferring static electricity from the air. Yeah. So you can't make energy out of nothing. There are some examples where you can turn matter into energy. Can anyone give me an example of that? Under what circumstances can we turn matter into energy?
A windmill farm?
Okay, that's generating electricity through the use of matter. What about combustion? Putting gas in your car, do you know how that works? You're burning the gasoline, burning something, burning wood. You are releasing energy from that matter, essentially splitting the wood apart into the particles that make the smoke and the ash and releasing the energy inside of it. Okay? All fossil fuels follow this process. Okay? You're essentially making energy through the destruction of matter. So that's one way that we can do that. So what they were doing was not making electricity out of nothing. Most likely what they were doing was using the nail to capture static from the atmosphere and then transporting it through the copper wire and the vinegar to the light bulb. I seem to recall hearing about the classroom experiments that do something like that. But I don't spend enough time on the subject to actually have experiments like that in my class. Okay, so any other questions on this concept? The most important conductors, like in military hardware, Apache attack helicopters, stuff like that, they have gold wiring, not copper. Why? Because in a $50 million attack helicopter, you don't want to have an electrical issue. So you put the best stuff in there. Even if it might get shot out of the sky, better that it get shot out of the sky than it crash and kill your soldiers because you were cheap on the material, right? So we put the best stuff in the most important equipment. Okay? Good deal. Now, let's talk about that mass in more detail. We talked about the number. We talked about its position on the chart. We talked about the columns having to do with the valence shells. Let's talk about that mass. The atomic mass is dictated by what again?
Total number of protons.
Total number of protons and neutrons, and also technically electrons, right? Which is why some of these have real weird decimals going out to the fourth place here, because you have to take into account the total mass of electrons as well, and that's a very small amount of mass. But for the most part, you're right, it's protons and neutrons. How am I supposed to tell how many neutrons are in my atom?
By subtracting the atomic mass by the protons.
And the protons, I know the number of protons because of
The atomic number.
the atomic number. If I subtract the atomic number, aka the number of protons in the nucleus, from the atomic mass, that tells me how many neutrons are in that mass, or in that nucleus, right? Good. Okay, so that's how we figure out the mass of our atom. Now, there are given masses for all of these atoms. For example, iron, 26 protons, 55 mass. Subtract that and you get the number of neutrons, you get the idea. That's a general rule for the ones that end up having lots and lots and lots of electrons. It starts to get kind of a fuzzy rule, but we're going to take it for granted within the bounds of this class. I'm not going deep into chemistry here, okay? What if I mess with this a little bit? What happens if I add a proton to a nucleus? It becomes a different what? Atom, bingo! I changed the number of protons in my nucleus. I have a totally different atom. Thank you. What happens if I change the number of electrons in my atom? What do we call that? A negative what? There is a special word. There's a kind of bond named after it. Huh? An ion. I get an ion. And yes, it can be a negative ion if I'm adding electrons. Or it could turn into a positive ion if I'm taking away electrons. But regardless, I will get an ion if I change the number of electrons in my atom. So I get a different element if I change protons. I get a different charge and therefore become an ion if I change the number of electrons. What happens if I change the number of neutrons? It stays the same. Does it? Aaliyah, what do you think? You think it stays the same? We call it the same name? It doesn't change its name at all? You're right. Okay, it doesn't change its name. It stays the same element, but something has definitely changed. What number have I changed by introducing new or taking away neutrons? The mass has changed. So, my mass has changed. Not all elements are cool with that. Matter of fact, a lot of them aren't. If I change the number of neutrons and therefore the mass in my nucleus, it becomes what we call an isotope. Okay? And you've got two different flavors of isotopes. Okay? You've got stable isotopes, which really don't care much. I know I'm adding a personality to them, but that's just so you can get the idea. Okay? They don't really respond that much. Then you've got unstable isotopes, and they care a whole lot. They fall apart, literally. Okay? Stable isotopes, something like carbon. Where is carbon on my periodic table? Someone find it for me. I heard several numbers there. What was that first number I heard? 6? It's number 6, meaning it has how many protons? 6. Okay. It's right there. 6 protons. What's its mass? Someone close to here, read that for me. What's the mass of carbon? 12. So, but if it has 6 protons, how many neutrons does it have? 6. See that math? Does that track? You all keeping up with that? Perfect. So there exists an isotope, a very common isotope of carbon called carbon-13. What's changed? The number of neutrons has changed by what? 1. Have I added or taken one away? I've added a neutron. Carbon-13 is an isotope of your normal carbon that has 1 extra neutron, and it doesn't care. Our atmosphere is filled with carbon-12 and carbon-13. As a matter of fact, my master's thesis was measuring the ratio between carbon-12 and carbon-13 in microfossils to figure out how much rainfall occurred in an area over 600,000 years. Because carbon-13 is just the tiniest little bit heavier on Earth because of our gravity than carbon-12 is, it prefers to fall in rain over carbon-12. And so the more carbon-13 you have, the more rainfall that area had. Same thing is true for oxygen-16 and oxygen-18. Slightly heavier falls first, more rain. So we can make interpretations of things like paleoenvironment just by studying the ratio of these isotopes that we encounter, which is pretty cool. Okay? A little bit more of that detective work to figure out the history of our planet. Okay? Okay, so that's carbon. And there is also, by the way, an isotope called carbon-14, which has how many more neutrons? 2. It's got 2. This one is less stable. It does, in fact, fall apart eventually. Not in a terribly catastrophic way, though. It's not a huge deal. However, the way that we make carbon-14 is through the burning of fossil fuels. Carbon-14, the isotope, only is generated when you burn fossil fuels, be that wood, coal, natural gas, or oil. Okay? So if you look at a ratio of carbon-14 to all the other types of carbon in the atmosphere, from the 1700s to now, it looks like a hockey stick. It's skyrocketed because the quantity of carbon that we've been outputting has been predominantly carbon-14. Your lungs don't really notice a difference, but the environment sure does, because it responds to carbon-14 in slightly different ways. But we'll talk about that at a later time. Now, let's talk about unstable isotopes. These are the fun ones. These are the ones that don't like being changed. The ones that you take away an atom, or excuse me, a neutron, or you add a neutron, and they just can't handle it. Let me give you an example. Uranium. Where is uranium on my periodic table of elements?
$92.
92. You might see it right here. Yeah, 92. Good. So it has 92 what? Protons. But its mass is, help me out here. No, someone closer?
238.
238. Good. So it has way more neutrons than it does protons, right? There exists several isotopes of uranium. The one that we use the most commonly is uranium-235. What's changed between uranium, as we normally see it, and uranium-235? We've taken away 3 neutrons, and it can't handle it. It starts to fall apart. It starts blasting particles off this way, and that's what makes this an unstable isotope. It starts shooting off electrons and protons and neutrons every which way possible. You know what we call that? Radiation. Oh, sorry, is that what you were going to say?
No.
Oh, what were you going to say?
I thought it was called decay.
It is. This is radioactive decay. Okay? But the material that's being blasted off is called radiation. Whenever you go outside and get a sunburn, you're absorbing radiation, except it's being blasted away from the sun as the sun is ripping apart particles, right? Some of the stuff that the sun rips apart gets thrown at Earth, makes it through our atmosphere, interacts your skin and gives you a nice tan, okay? How nice of that one photon to impact your skin after traveling through space for 8 minutes to hit you, right? Okay. Here on Earth, though, when you get radiation generated from something like uranium-235, it's not as nice, okay? You get a sunburn, mild radiation poisoning. Yeah?
What about X-rays? Don't they use radiation?
X-rays are a form of radiation. Yeah, we can purposefully generate radiation for certain things, like X-rays that will bounce off of materials in your body like bones, and you can collect those returned X-rays and generate a picture of what your body looks like on the inside, okay? But uranium-235, very unstable, constantly blasting radiation off of itself, okay? Now, eventually, it will reach a state of stability again, because in general, remember this, I mentioned this earlier, all things in nature are seeking a state of stability. It's going to keep coming up, like I said. That uranium is going to decay by blasting particles off of itself until it reaches lead. Where is lead on my periodic table of elements?
Column 4?
Hmm?
Column 4?
Column 4, all right. Anyone, can it? 82, good. And its mass? 207, okay. So we've gone from 92 to 82. We've lost how many protons? From 92 to 82. Therefore, we've lost 10 protons. We have gone from 235, because we're talking about the isotope, to 207. So we've lost how many neutrons? Huh? What's 35 minus 7? That's an easy way to do that. 28. Bingo. We've lost 28 neutrons, and who knows how many electrons total, okay? Because there are multiple shells to take into account. But by the time we have gone down to 82 protons and 207 neutrons, we've blasted off so much radiation, we become a totally different element. Now we're finally stable. Okay? At that point, it stops being radioactive and becomes a new stable element. This is radioactive decay. An unstable isotope blasts particles off of itself until it becomes a new stable element. Now, this is very useful in science for one particular reason. We use this for something called radiometric dating. You ever heard that term? You ever heard the term carbon dating? Yeah, that one is kind of filtered through our society a little bit easier. Okay? It's because there are a lot of complicated terms for radiometric dating. Okay? So carbon dating is kind of the one that society latched onto, except that's not actually accurate because carbon dating relies on determining ratios of these things and their decay rates, which becomes really inaccurate after about 50,000 years. Anything past 50,000 years, we don't even touch carbon. We don't even consider carbon because it's inaccurate. Past that, yeah, we use things like uranium and potassium and thorium isotopes, okay? To go back millions and billions of years. So how do we do this? Well, it turns out radioactive decay is consistent. Uranium-235 will decay to lead-207 at the same rate forever. And that's true here. It's true on Mars. It's true in the sun. And it's true on the other side of the galaxy. And it's true on a planet on the other side of the universe. Radioactive decay is consistent, which means we can make a system of dating things with it. So we use this thing called a half-life. You ever heard that term? A half-life is the amount of time that it takes for any quantity of uranium or any other radioactive element to decay to its daughter isotope, that is the stable isotope, okay? The stable version that it's going to eventually. So if I have a dinner plate filled with yummy, yummy uranium-235, after one half-life, half of it will have become lead-207. After another half-life, how much do I have left? It's a sneaky, tricky question. Huh? 103.5. Are we on a radio station? Where's that number coming from? Oh, no, that's the mass. I'm talking about, that's the mass of one element, of one atom. I'm talking about a dinner plate full of the stuff, right? After one half-life, I have a 50-50 split between lead and uranium. After another half-life,
Just lead.
oh, that's the trick. No, because the first time I split the whole dinner plate in half. I have a 50-50. After the second half-life, I'm only taking into account the remaining uranium after the first half-life. So I split the remaining 50% in half. So after two half-lives, I have a 25-75 split. After a third half-life, I only have 12.5% of the original uranium left. After another half-life, I have 6.125, something like that. Okay, but you get the idea. How many times can you divide something in half before you have nothing? Pretty much infinitely. Eventually, you will, of course, be down to one atom. And at that point, you could split that atom, but then you'd have problems, right? So, pretty much infinitely, which makes this a perfect method for dating objects. We measure the ratio of lead to uranium-235, and we know exactly how many half-lives have passed. What is the half-life? It's about 207 million years. Yeah, I know. So if I look at a rock and I do an analysis of lead versus uranium, then I can say, based on the ratio here, 207 million years have passed since this rock was made. And that, my friends, is how we can say things like the Earth is 4.543 billion years old. My tongue got tied on that, okay? How are we getting those numbers? Radiometric dating. So cool. Of course, there's another way we can use unstable isotopes, a way that's a little less contributive to society. That's how you make a nuke. All the energy that is released slowly over time, all of that radiation that those little isotopes of uranium are releasing, if you figure out a way to release all that energy at once, that's how you make a nuke. It's called splitting an atom. You already have an atom that's unstable, pretty easy for it to fall apart. All you need is the right trigger, and then you can release all that energy all at once. That's where you get a nuclear weapon. It's also the same concept behind nuclear reactors, by the way. Okay? A nuclear reactor essentially takes a whole bunch of unstable isotope material, puts it into a vessel, a big old room filled with water, and as those unstable isotope cores of metal, like uranium, are pushed closer to each other, they're generating more radiation by bouncing off of each other. They bounce the radiation off each other. It increases the heat in the room, which vaporizes the water, and that steam turns a turbine, which makes electricity. That's how a nuclear reactor works. You just keep pumping more water in that room, and you keep making more steam, and you have a self-sustaining power system based entirely off of the simple fact that these two cores of metal are unstable elements. It's like free energy. It's fascinating. Honestly, nuclear energy should be used more. If we ever want to get to space, we got to use nuclear. Okay. Going back to the subject of bombs for a moment, there haven't been any nuclear weapons detonated on our planet for a while. Last time they were used in violence was to end World War II. I lived in Japan for 4 years. I have been to both blast sites, the Nagasaki and Hiroshima bomb site locations. They still keep certain parts of those cities in a condition so that you can see the devastation. And they have museums set up so you can appreciate how terrible it was. What does radiation do to a human? Radiation essentially is a super energized particle, and as it blasts through your tissues, it is destroying your DNA. Your DNA, that is the coding of your body to maintain itself. As your tissues are destroyed and your DNA is destroyed, there is no replacement tissue coming. There is no replacement cell being manufactured because the code to do so has been destroyed. Therefore, your body literally falls apart. You essentially melt in the face of that much radiation. It's not pretty. These museums in Japan, they have pictures. It's not pretty. So a nuclear weapon has not been used in violence for a long time, but until not too long ago, there was still some testing. No one actively tests them anymore. The largest nuclear weapon ever detonated, by the way, fun fact for anyone that's interested, is called the Tsar Bomba. Anyone heard of this one? Yeah, a few of you? The Tsar Bomba was blown up on this banana-shaped island above Russia right there. Right there. The largest nuclear weapon ever detonated, ever tested. It set off earthquake sensors across the planet and shattered windows all across Europe. A standard nuclear weapon, you would need to plant one in pretty much every major metropolitan city to take out a country. You would only need about 5 Tsar Bombas to take out civilization across the planet. Which is why, as soon as that test occurred, the international community came together and agreed that it would never, ever, ever, ever be used, no matter the circumstances. But you know everyone has them. There's no way everyone doesn't have those. If they existed at any one time, you got to assume everyone has them. Right? Okay. Any questions now that you have your background on matter, on atoms, on isotopes, on ions? No? Wow, you all are getting it? Yeah.
So unstable isotopes. If you added a neutron, would it make it unstable?
If you added a neutron, it definitely could. Definitely could, yeah. Adding or taking away neutrons can make it unstable for sure. It depends on the element. Anything else? Yeah.
So how you were saying, the carbon in the atmosphere makes it rain more places?
No. The amount of carbon in the atmosphere doesn't make it rain. But when it does rain, the heavier, aka with more mass, isotopes tend to fall first. Let's use oxygen as an example. Hold on just a moment. There are 2 isotopes of oxygen, 16, which is your normal oxygen, and 18, which has 2 more neutrons. Oxygen 18, here on Earth, because we have gravity, is heavier. And therefore, when the H2O forms in the atmosphere, right, O18, being the heavier, tends to fall first. And so if I were looking at the isotope ratio of a plant, right, and I would see that it has a higher ratio of oxygen 18 to 16, I would interpret that as meaning it is in a higher rainfall area, probably closer to the equator. Right? It's a fair interpretation I can make. Yeah?
Is that how we can smell rain?
Smell rain? No, the smelling the rain thing, rain doesn't really generate a scent. But depending on the environment you're in, you will be able to catch a whiff of whatever's on the wind. Usually, whenever rain falls on an area, the plants, the soil, they'll generate some sort of gases, or there will be some other substance like dust. A lot of the times is puffed kind of up in the atmosphere. So smelling rain doesn't actually have anything to do with the rain itself. Just a change in the atmosphere, like the change in pressure as rain is approaching, bringing scents from where the rain is already falling is typically what that is. Great questions. Thank you for asking questions. I love it. What else? Questions over here? No? Clear as mud? Yeah? All right. All right, well then let's move on. Let's talk about minerals. Now that you understand matter, matter makes minerals. Geology is more or less solid chemistry, folks. You're going to learn that today. So what is a mineral? There are lots of definitions for a mineral. I mentioned last time I held up my protein shake. It says good minerals, or some variation, right? All the minerals you need for a healthy diet. So you've got your healthcare definition of mineral, which is essentially vitamins. Okay? They treat it more or less like vitamins. Then you've got your mining definition of mineral, which is anything that you can take out of the ground for economic value. That includes oil, by the way. Okay? Anything you can remove from the ground for economic value is a mineral to the mining industry. But as far as geologists are concerned, there is a definition. I mentioned to you last time that there were 2 things you needed to know word for word. The first one I gave you last time was the principle of uniformitarianism. The second one you're getting right now. That's the definition of a mineral. Have this word for word, because if you change one word in this, the meaning changes. And by the way, if you were to Google definition of a mineral, it would give you something slightly different. Don't do that. Use this definition. A mineral is any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. How about I say that again? A mineral is any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. Change one of those things and the definition changes. Okay? It's not a mineral anymore if you change any of those things. And any of those things are a mineral. Okay, so the difference between a mineral and a rock. Do you remember what I told you last time? Who remembers the analogy I gave last time? I think I used you as an example of this. Yeah. The chocolate chip cookie. A mineral is not a rock, but a rock is made of minerals, right? Remember I said that? Here's the example I gave. Faith, right? Great. Let's use a different example. I hand you a little handful of salt and say, have a chocolate chip cookie. Is that a chocolate chip cookie? No. Would you treat it like a chocolate chip cookie? No. It's just Mr. Hart being weird again, right? But salt is in chocolate chip cookies. It's an ingredient of them. It would be weird to call that salt a chocolate chip cookie, though. You need a whole bunch of other ingredients first. That's the same thing with minerals and rocks. Here we have a rock called granite. You've probably heard of granite before, right? We use it for building materials all the time. You might even have countertops in your house made out of granite, although we'll talk about that later on. They may not be actual granite. You'll learn about that later. Okay? But granite is a rock made out of minerals, commonly quartz, hornblende amphibole, and feldspar. I've got a piece of granite right here, made out of all those minerals. This is a chocolate chip cookie. Each of its individual components are the ingredients. Minerals. Okay? That's the difference between a rock and a mineral. So from this point forward, we will be using those words in their proper context. Fair enough? Good. So how do we tell minerals apart from each other? They have properties, as it turns out. And you're going to be using those properties to identify the minerals in our lab that you're getting today. Yay! Excited. Yeah. Okay, good. All right, so the properties that you need to know. Let's start off. You've got your optical properties. That is the way that your mineral interacts with light. Okay? So, for example, the way that light reflects off of it, the way that light passes through it. I'll give you each one of these a little bit more detail in a minute. You've got the crystal shape, also known as the crystal habit, also known as the crystal form. All three of those terms mean the same thing, the shape that your mineral naturally grows into. You remember what I said about geology? It's essentially solid chemistry. Well, when you take atomic bonds and you make a structure out of it, it makes a shape, a geometric shape. And as you add more mass to it, as you keep repeating those same patterns, that geometric shape gets larger until it's large enough for us to see. And it makes natural geometric shapes like this. How cool is that? Pretty cool. All right, then you've got stuff like the density, which you will not be measuring in this class. That would be an exercise that would be cool, not essential for you to learn how to do, though, and you don't need it for identification purposes typically. And you've got stuff like taste. Please do not taste every mineral I give you. There are a few on your test kits that, yes, taste will be useful. But please do not taste every mineral. Along the back of this room, you'll see that I've got rows of trays of rocks. Okay, so all of those trays of rocks and minerals do not taste numbers 18 or 37. Number 18 and 37 are, in fact, toxic, and if you do accidentally taste them, let me know, and I will contact poison control. Okay? One is a lead sulfide, and the other is an arsenic. Do not taste them. All right? If you touch them, there's a sink there, so you can wash your hands. That's 18 and 37, the only ones that are unsafe to actually taste. Okay? Then you've got your texture. Okay? Texture is going to be the way that it feels in your hand. Okay? It might feel a little soapy. It might feel like dirt. It might feel like you're rubbing dirt in your hand. Okay? You've got stuff like hardness. Okay? To test hardness, you're going to get a piece of glass in each of your kits. We use something called the Mohs scale of hardness. It goes 1 through 10. It's a scale of relative hardness. Okay? There's no actual numerical hardness associated with these numbers, only relation to other things on that same scale. So for example, glass has a hardness of 5.5 on the Mohs scale of hardness. So when you scratch the mineral on your glass, the only thing you're going to record is it greater than or less than 5.5? If it scratches the glass, it must be harder than 5.5, greater than 5.5. If it doesn't scratch the glass, it must be less than 5.5. Perfect. That's all you need to give me. Okay? Then you've got magnetism and other stuff like that. Each of you has a magnet in there in your test kit to test. It could be useful. And then there's effervescence. What is effervescence? You have a small little vial of liquid in each of your test kits in front of you, by the way. These are your test kits, these blue lids. Okay? If you open that up and pull it out, you'll see that there's a tiny little vial of liquid. That is hydrochloric acid. It's not water. Don't treat it like water. It is hydrochloric acid. Diluted, it will not burn your skin. But if you accidentally get some on your clothes, it will dissolve the fabric. So mind yourself. I have lost more shirts to hydrochloric acid in my life than my wife ever wants to know. Right? She hates hydrochloric acid. She hates that I have to use it. Actually, so funny story. I actually got delayed by TSA one time when I was trying to fly off to do some field work because they tested my bag. They did a random chemical swab in my bag, and they got hydrochloric acid residue, which I suppose is used in making certain types of explosives. So they pulled me aside, and I was in there for an hour getting questioned. And it took me that long to convince them that hydrochloric acid is a tool that geologists use all the time, and that's why it was in my bag. I didn't even have any in my bag. They just found residue in my bag from the last time I did field work. So, yeah. But this stuff is totally safe. Just if you get some on your fingers, it's not going to matter. It might feel a little slick. It's just dissolving the outer layer of skin. Okay? That's all it's doing. It won't hurt. And the outer layer of skin, it's dead anyway. You don't need it. Yeah. You may. All right. So those are the different properties. Hi. What's up?
I'm fine. Telling you from academy cards.
Okay.
Okay, so your schedule, I was working with my schedule, but it has to work with yours, Brian, and Shelby's schedule.
Hi.
Because we're doing the interview.
Great.
And it's in October. October, our schedule will change. Is yours still going to be?
No, I'll be teaching Monday, Wednesday. Same time, but Monday, Wednesday.
Okay. So we thought, it's like 3:30, is that too late for you?
Yeah, if I know far enough in advance. So it's not,
Okay,
it's not
so 3:30, any Tuesday or Thursday, and
after fall too. Yeah.
so I give the time to.
Oh, we do have a
Debbie
video.
and they tell me that they're available. Now, the last week of October, I'm gonna be in office, so I can't do it that week. But the first,
If you tell me a date, I'll give you a hard answer.
Okay, all right, okay.
That's the glass.
I'll just let you know.
Yeah, that's
No worries. No worries.
Can I stop?
I mean, in general, yes.
Dale.
Yeah. No, I'll be fine.
Okay.
I'll be fine. In general, the answer is yes. But once I have the actual date, I'll be able to give you a hard answer of yes or no.
Okay.
All right. Yeah. Thank you. All right. Yeah. What's this? Oh, yes. I'm sorry. I didn't know what that meant. Yes, May. Yes. Okay. So we're going to talk about each one of these properties in a little bit more detail, starting with those optical properties. The manner in which light interacts with the surface of your mineral is called luster. Okay? And there are lots of different types of luster. It can have a pearly luster. That one's pretty easy to comprehend, right? It looks like pearl. It can have a glassy luster, also known as a vitreous luster, by the way. Those two things mean the same thing, vitreous, glassy. It can have an earthy luster. It kind of looks like it's made out of dirt. Silky, greasy, like someone sprayed it with cooking spray. Okay, that's what a greasy luster looks like. Metallic, it can look like a metal. That's a metallic luster. Okay, so that's your first one. Then you've got your optical property in as much as the translucence. Okay, is it translucent, transparent, or opaque? Who can tell me the difference between transparent and translucent? Say it louder.
transparent. You can see all the way through.
Transparent is you can see light and an image through it. Translucent, you can only see light through it. You can't see an image. Yeah.
What would frosted glass be?
Translucent. Frosted glass, you can see light through it. Maybe, depending on its level of how frosted it is, maybe you can see a shadow if someone's like directly on the other side, but you can't see an image. So that's translucent. And then you've got opaque, which no light can go through it at all. Okay? And then there's color. Now, it's going to be very tempting for you to try and use color as your main method of identifying these minerals. Don't do that. That's the first trap. Why? Well, because color is dictated by the elements present in that mineral. Believe it or not, there are way more minerals than there are elements, and so they end up sharing a lot of elements. Okay? So you may have two totally different minerals that share the same elements and have the same color. Or you'll have two copies of the exact same mineral that have different colors. Okay? So don't use color as a primary method of identification. At best, we use it as a tiebreaker, which is why I still have you record it, because it's worth noting. But don't use it first. Okay? streak. Each of you in your test kits, and by the way, if I need to put out more test kits for this, I can. I just kind of encourage you to do your lab work as a team. Form a group with whoever's around you, or if you have people you already know you work well with in the class, do that, okay? But you have in your test kits white porcelain plates. These are called streak plates. You also have black ones in there, by the way. You'll scratch your mineral on the streak plates to figure out what the streak color is. The streak color is often what we use to interpret what the mineral's color is at the atom thick level, okay? So I'll have a mineral that looks gold as a mass, but if I scratch it on my streak plate, it could come up black. I'm looking at just a layer of that mineral a few particles thick. And so that can help me understand what the true color of that mineral actually could be. Okay? So, streak color, that's what you'll be recording. Okay? Then you've got crystal shapes, also habits, also forms. All of those mean the same thing. Okay? This is the original shape of your mineral. That is the shape that it grew into, that it had before it got broken. Many of the samples you'll be seeing are broken. As it turns out, it's difficult to get completely unbroken versions of every mineral, at least in a quantity that I can use for you all in your labs. You're less likely to come across the unbroken ones in the world anyway, and so it's better for you to be able to identify the broken ones as well. Okay? So, some examples. By the way, there are dozens of crystal shapes that can form, and you'll have a link to a website that you can go to see all of those for the lab. Here are a few examples. Magnetite. These are formed in octahedrons. They kind of look like two pyramids that have been glued to each other. Dodecahedrons. If you've ever heard of the gemstone garnet, okay, they form dodecahedrons like this. These 12-sided shapes, they were not cut into those shapes. These are the shapes they naturally form. Dodecahedrons. And then cubes. This is the mineral halite. You probably know it by a different name, salt. This is the mineral halite, okay? It forms cubes naturally, okay? Next property is tenacity. That is the way that it responds to stress. How does it break, essentially? Does it shatter? Well, then it's got a brittle tenacity. Does it bend and then keep its shape? Well, then it's got a malleable tenacity. Is it elastic? That is, can you bend it and then release the pressure and it'll snap back to its original shape? That's elastic tenacity. So you'll see how it responds to stress. Now, you're not going to be hitting any of my rocks or my minerals with a hammer, okay? You're going to be going off purely what it appears, the way that it responded when it was broken. All right? Okay. You've got the mineral strength, like I mentioned earlier. We have the Mohs scale of hardness. It goes 1 through 10. 10 being diamond, 1 being talc, which is the softest mineral we know of. It's the mineral that you make baby powder out of. Okay? Okay. So on a scale of talc to diamond, 1 through 10, with glass being 5.5, you're going to be measuring each of your minerals on your glass plate. I'm going to take this opportunity to give you a little bit of a safety tip. All glass and all streak plates always need to be face down on the table, because some of them are sharp. Some of them have little nicks and jagged edges. And if you're holding it like this and you're trying to really dig into it with a mineral to see if it'll scratch, you could break that glass on your hand. I don't want to deal with that. There's a first aid kit from the 80s over there. I'd rather not open it. I've never opened it. I've been afraid to. Okay? So don't do that. All right? So keep all glass and all streak plates face down on this table. And honestly, the black background of the table makes it easier to see what scratch you're leaving on the glass anyway. Okay? All right. Mineral cleavage. I leave this one for last because, or one of the last ones, because it tends to be the most of a doozy for you. Cleavage is the manner in which a mineral breaks based upon its internal atomic structure. What do I mean by that? Remember that all minerals are an aspect of solid chemistry. They are atomic bonds that form and make a solid. Not all bonds are equally strong, though. If I have hydrogen, carbon, and oxygen all combined together, perhaps the bond between carbon and oxygen is stronger than the bond between hydrogen and carbon. And if that's the case, when I exert pressure on that bond, which one is going to break first? The weaker one. When stress is exerted on a series of bonds, the weaker ones always break first. So, when a mineral has cleavage, that means that it is going to preferentially break along the planes, the surfaces in that... What's going on out there?
Somebody stomped.
Somebody's what?
Stomped.
Stomped? Okay. Are they okay? Or are they just messing around?
I think there was.
All right. There have been fights break out there before, so I like to check. The planes of weakness in your mineral caused by those weaker bonds are going to break first. Okay? So that's what cleavage is. Now I'll tell you about the different ways that you can observe cleavage. When I started this job 5 years ago, I was like, cleavage is really difficult to just tell people and have them get it. So I wanted to get some physical, actual, hard, tangible thing that you could all see and experience to understand the concept. And I spent weeks trying to find something. Nobody had ever made one. So I designed these using 3D software, and I 3D printed these. And I have a patent outstanding on these. It hasn't made its way through the patent office yet. It's currently pending. But these are 3D cleavage models, okay, that I'll pass around the class. I'm going to show them to the camera first, and then I'll pass them around so you can see what I'm talking about. When you have one plane of cleavage in a mineral, that means that it's going to break along flat surfaces in one direction. Okay? Whatever the original shape of my mineral is, it will break along one direction on these flat surfaces because that is the plane of the weakest bonds. Okay? So, one plane of cleavage. I'm going to pass this around starting over here. Yeah, just take it, pass it down, and then table to table, making its way down. Okay, now, after the one plane of cleavage, it gets a little bit more complicated. Because after one plane of cleavage, all of a sudden, we need to start talking about angles. Because you can say two planes of cleavage, but what that means is it's breaking preferentially along one direction, or along two directions, right? No longer just one. That means that it could be going at any certain angle. Those two planes could intersect at any angle. Within the bounds of this class, I'm only going to ask you if the two planes, or more planes, are intersecting at about 90 degrees or not. You don't need to whip out a protractor. You don't need to figure out the exact angles. All I'm asking for two or more planes of cleavage, does it seem to be at 90 degrees or not at 90 degrees? That's all you got to worry about. Two planes at 90 degrees, camera, hi, right here, thank you, looks like this, okay? Where you have 1 and 2. And about what angle does that look like they're intersecting at? Huh? Yeah, this is two planes at about 90 degrees. Okay? Careful, the magnet comes loose on one of those sides. I have to re-glue it. Okay, two planes not at 90 degrees looks like this, where you have one surface like that and one surface like that. The two surfaces that are breaking in flat angles are not at 90 degrees. This is obviously an acute angle. This is obviously an obtuse angle. Clearly not at 90 degrees, but still only two planes of cleavage. Okay? jostle the planet there. All right, so that's 2 planes. Let's talk about 3 planes. 3 planes of cleavage at 90 degrees is going to make a cube. Here we have 1 plane, 2 planes, 3 planes at 90 degrees. 90, 90, 90. Makes a box, makes a cube. Okay? And when this cube breaks, because it's breaking in 3 degrees, or 3 planes at 90 degrees, it's going to break into smaller cubes. Okay? 3 planes, 90 degrees, makes a cube. Three planes not at 90 degrees. It's going to be like a cube that I was going to say an artist on drugs had fun with, but you know, it kind of does. It's like a squished, a squished box, okay? Like a real new world perspective on what a box would look like if you asked an AI to generate one, okay? Yeah, you may, okay? So we've got 1, 2, 3 planes still, but none of the angles between them are 90 degrees. We call this a rhombohedron in geometry, right? And it breaks into smaller rhombohedrons if you were to break this object. Okay? 3 planes, not at 90 degrees. And then finally, that's already been a lot, huh? But this is the last one. Okay, this is the last one you could potentially see in my class. There are way more complicated cleavages than this one, but I'm not giving you anything with more than 4 planes of cleavage. Okay, 4 planes of cleavage. It's going to look like this, where you have 1, 2, 3, 4. Okay. Okay. Now I'm going to address the elephant in the room. I've been saying 1 plane, 2 plane, 3 plane, 4 plane. But Mr. Hart, you said 4 planes of cleavage, but there are clearly 8 sides on this thing. You said 3 planes of cleavage for the box. There's clearly 6 sides on that thing. What are you talking about? Let me help you out here, okay? I'm talking about planes, not sides. This plane and that plane are the same. This plane, that plane are the same. They are 2 different sides, but they are exactly opposite each other on the object and going at the same angle, aka the same plane. So while this object has 8 sides, 4 of them are exactly parallel to the other 4. Therefore, we only have 4 unique planes of cleavage. The same thing is true for 3 planes and 2 planes. It's okay. I mentioned one of them has a loose magnet. As long as we don't lose that, we're fine. All right. Any questions on that? It's going to be tricky. There's going to be a little bit of a learning curve because you have to see it enough times for it to make sense, which is why I have made many videos on my YouTube channel to show you all every possibility that you could be seeing on the lab. There are 51 possible minerals on your lab. You'll have to identify 24. I give you a list of 24 for the lab out of the possible 51 that they could come from. But I give you all of the properties and videos of me testing all 51 on my YouTube channel. You also, for those of you here in person, have the benefit of seeing all 51 there at the back of the room. Boxes 1 through 51 back there correspond to the practice set for Lab 1. Okay, so you get to have as much hands-on or video experience with seeing what these different cleavages and other properties are as you want before you even start the lab. Okay, if you're confused about what 3 planes of cleavage at 90 degrees looks like in real person, look on the practice set, find one that has that, and then watch the video or go find it at the back of the room and see for yourself. Get that experience that you need / want before you start putting work into the lab. Okay? Any questions about cleavage? Yeah?
This isn't a question about this, but kind of a reminder. Which ones are do not lick at all?
18 and 37, do not like. Faith, which time did your other class start?
It started at 50, but that schedule got changed.
Oh, your schedule did get changed? Okay, good. I was going to call them today and try and figure that out. I'm glad you got that done. Good job. Okay. When a mineral does not have cleavage, it instead breaks with fracture. And there are several different types of fracture that you'll see in the Lab 1 PowerPoint, which is essentially an overview of all of this stuff again. I list all of the different types of fracture there. An example would be quartz. Quartz does not have a cleavage, but it does break in this sort of ripply, sort of scooped out pattern. We call that conchoidal fracture. You may have seen glass do the same thing. Okay. Then there is density, which is a measure of mass per unit volume, a very important characteristic, very important property, but not one that we will actively measure in our class for time reasons and because it has no practical value for you unless you are actually going into geology, right? So for very few people, knowing how to test for density is important, but for the vast majority of you, how many of you are going to be able to test density out on your camping trip where you pick up a rock, right? You probably won't. All right, other properties. I already mentioned taste. Please don't taste everything. There's texture. How it feels could be very relevant to your final decision. Smell. Certain minerals like sulfur do have a unique smell. If you've never smelled sulfur, I've got a big chunk of it in the back of the room up there on that shelf. It's that big bright yellow one. It smells like rotten eggs. Now you really want to smell it, don't you? Yes, I can see it. Okay, and then there's magnetism. You have a magnet to test for magnetic minerals, and then you have the hydrochloric acid to test and see if it's effervescent. I'll give you this for free. 2 of the minerals on this lab are effervescent. They will fizz. One will do so very easily. The other one takes a little bit of effort. You're going to look at it and think, this should be fizzing. It has the properties of one of the minerals that should be fizzing, but it's not. Well, you take a little piece of your glass, and I do this for you all in the video if you're watching this online. Scratch off a little bit of dust. Then just make a little pile of mineral dust there. I've got enough of this stuff. I'm not worried about that. Okay, and then put some acid on that, and it should fizz if it's the mineral that you're thinking it is. All right. Thank you. Any questions about properties? No? Okay. Let's keep on moving then. There are over 4,000 minerals. We have 8 weeks. Who's ready? You ready? Jackson, I knew I could count on you. No, we're not doing 4,000 minerals. Don't worry about that. Okay? You're only going to be learning about 51 and identifying 24. Okay? But there are a lot of them, and we discover more all the time. Okay? Our planet has a wide diversity of mineral content that makes up its structure. And that's only what we can see within the very limited scope of what we can access here at the surface. Who knows how many other possibilities there are that are even deeper underground that we can't access, at least not yet, right? So we separate all of these minerals in general into what we call silicates and non-silicates. Silicates are formed around a central structure called a silicon tetrahedron. We'll talk more about this concept when we learn about volcanism. But when magma is cooling off, the first bonds that form in that magma to start solids are silicons and oxygens. They like each other a heck of a lot. Okay? They bond super easily. They're also extremely common on the surface of our planet. Okay? So silicons and oxygens come together. We get 1 silicon and 4 oxygens in a covalent bond. Okay? So this is our silicon tetrahedron. Everything else attaches to that to make silicate minerals. We'll talk about non-silicates here in a little bit. For now, we're going to focus on silicates because they are the most common. All right? So silicate tetrahedrons will form bonds given enough time. While my magma is still hot, they are going to stay as individual tetrahedrons, independent tetrahedra. Okay, and they're going to form some minerals that way. As our magma starts to cool off and more bonds are forming, we're going to start seeing single chain and then double chain tetrahedrons attaching to each other. And then as our magma cools off even more, we get sheet structure tetrahedrons and then three-dimensional framework tetrahedrons. The mineral olivine has a chemical recipe of magnesium, 2 irons, and what's that? SiO4.
Silicate oxygen.
Silica and oxygen making what? What is the structure that has 1 silicon and 4 oxygens called?
Sheet structure.
Silicon tetrahedron. Silicon tetrahedron, all silicates are attached to. So what makes this mineral olivine? Olivine, the fact that it is iron and magnesium attached to that. Okay? Every now and then, we're going to see some interesting things happen around the silicon tetrahedron structure. For example, let me back up here real quick. The further along we get in this process, the lower the ratio of silicons to oxygens gets. Here we have a 1:4. 1 silicon, 4 oxygens. Moving down through here, we eventually reach a 3:1 ratio, where silicons are sharing oxygens, and therefore there is a 3:1 ratio. And then finally, by the time we get to the three-dimensional framework, there are only 2 oxygens per silicon, which is why quartz has a net neutral charge. Because if you'll notice, backing up again, what do we have here? Our silicon has a 4 positive charge. Each oxygen has a 2 negative. But there are 4 of them, meaning that this whole structure has a net negative 4 charge, right? It's covalent. They're sharing all the electrons. But it has a net negative 4 charge. Perfect for positive metal ions to attach to, which is where we make those first, minerals, like olivine. But as our ratio of oxygens to silicons keeps getting lower and lower until finally we're at a 2:1, we have 2 -2 ions and 1 -4 ion. Those cancel each other out, right? Meaning that anything with that 2:1 ratio, aka quartz, being SiO2, has a net neutral charge. Quartz has a lot of fascinating properties, by the way. It seems lots of people are experimenting with this, but it seems that quartz has the ability to potentially store energy in it. And constructing an artificial framework of quartz that can hold a large amount of energy is something that a lot of people are working on right now. How cool would it be if we could start using quartz crystals for batteries? Pretty neat. Okay, now all of these different particles have different sizes and therefore can substitute for each other on occasion. That mineral I showed you earlier, olivine, had 1 magnesium and 2 irons. Well, it could just as easily have 2 magnesiums and 1 iron. Okay, because look at this. Let's see, magnesium and iron right here have the same charge, +2, and are about the same size of atom. So they can sub in for each other a lot with very little effect. I just hit my microphone. Sorry there if that blew anyone's eardrums out. Same thing is true, by the way, sometimes for silicon and aluminum. Occasionally, we will see those swap, and those make for some fun, interesting combinations. So the chemistry within these things is sometimes a little bit fluid, okay, depending on the situation, and again, depending on the heat and pressure present, that will affect the bonds. Okay. So let's talk about the progression of minerals that we see form. The silicate minerals. I'm going to differentiate these again. So we had our silicates and non-silicates. We've pushed aside the non-silicates for now, expanding out the silicates. I'm going to slice that in half again. We're going to get our light silicates and our dark silicates. Ferromagnesian for dark silicates, non-ferromagnesian for light silicates. What does that word mean, ferromagnesian? What do you want to, yeah?
Something has magnesium and iron.
Magnesium and iron. Bingo. Ferromagnesian, aka containing magnesium and iron. So ferromagnesian minerals, therefore, are the ones that have magnesium and iron. Non-ferromagnesian are the ones that don't have magnesium and iron. Okay? We also call these light silicates and dark silicates because minerals that contain magnesium and iron tend to be on the darker color spectrum. And the ones that don't contain magnesium and iron tend to be lighter colored. So let's start up here. And I'm going to add a little bit to this, actually. I'm going to add a little thing on here that's going to be, I keep forgetting I took my pens out. It's going to be very relevant to you next week. I'm going to add a temperature scale. As we go down this list, the temperature of magma that is forming these minerals is dropping. Okay? Doesn't mean a heck of a lot to you right now, other than the comprehension, the fact of temperature is falling and associated with the different types of minerals forming. But you're going to connect some big dots to this next week when we learn about volcanism and the formation of minerals. Okay, so say we have a hypothetical magma. It's cooling down. As it cools down to a certain temperature, the silicon tetrahedrons form. The silicon tetrahedrons are independent tetrahedrons because it's still pretty hot. But they start attracting metal ions to themselves to satisfy the electrical charge that it needs. Okay? So we start forming things like aluminum. Next, as temperature continues to drop, our silicon tetrahedrons start to form chains. We get things like pyroxene, then amphibole, then biotite mica. Are these lighter or darker in color? They're darker. Ferromagnesian silicate minerals form long before our light ones do. They form at higher temperatures. Then, once we reach a certain temperature threshold, we start forming those light silicate non-ferromagnesian minerals. Okay? So we get our muscovite micas, and then our feldspars, and then right there at the end, quartz, which is nothing but silicon and oxygen, because that's pretty much what's left. Okay? This is the general progression. Dark silicates to light silicates as temperature falls. So represented on this list are some of the most common minerals that you will encounter on our planet. And I'm going to talk about each one of those here for just a quick second. Feldspar makes up estimated about 50% of the crust of our planet. This is feldspar. Let me talk about feldspar for a second. It's so common, it's probably the most relevant to you, whether you know it or not. Okay? This is the crystal form of feldspar. I'm going to back up here for a second to give you a little bit more help with crystal form and cleavage. Feldspar is a fantastic example of this. This is the crystal form, the original, unbroken geometric shape of feldspar. Beautiful. It's twinned. Actually, what you're looking at is two feldspar crystals that grew into each other. We call that twinning. This is broken feldspar. Doesn't really look the same, does it? They are the same mineral, though. This geometric shape and this shape are very different. Do you see those flat, shiny surfaces? Clearly, this is a broken mineral, but it's got flat surfaces. What do we call that? Flat, broken surfaces are cleavage. Bingo! You're looking at cleavage planes. Okay? And how many are there? Well, there's one flat surface, 2, 3, 4 flat surfaces, but 2 of them are parallel to the other 2, so we must have how many? 2 cleavage planes. Look at you guys, you're getting this already. And about what angle are those cleavage planes intersecting at?
90 degrees.
Yeah, do we all agree that looks like it's about 90 degrees? Yeah? Let's show that to the camera. Those cleavage planes are intersecting at about 90 degrees. So the feldspar has 2 planes of cleavage at about 90 degrees. You know what? I'll pass this around so y'all can see that hands-on. Okay? Okay, so that are some of the properties of feldspar. Okay? Fantastic example of cleavage. Hardness scale of 6, pearly luster, glassy luster sometimes, depending on the type. There are 2 types of feldspar that you're going to see in my class. Okay? You're going to be seeing potassium feldspar and plagioclase feldspar. How do you tell the difference between the 2? Potassium feldspar tends to be, and remember, color is not a primary identifier, but tends to have a lot of the darker colors of the feldspar groups. Okay? But also, plagioclase feldspar has one distinct characteristic. When you look at its cleavage planes, when you shine it in the light, and I do this for you in the videos for my online students, when you shine the cleavage planes in the light, you're going to notice parallel striations, parallel grooves in the sides of your rock, or excuse me, of your mineral. Look at that, I did the bad thing. Okay? In the sides of your mineral, on those cleavage planes, you're going to see parallel grooves, and that's the easiest way to tell the difference between plagioclase and potassium feldspar. Then we've got quartz. Quartz comes in a wide range, okay, a very wide variety. You've got clear quartz, you've got smoky quartz, you've got milky quartz, you've got rose quartz, amethyst. How many of you knew that amethyst is a quartz? Good. Yeah. Amethyst is not its own type of mineral. It is a variety of quartz. What makes all of these quartz crystals look so different from each other if they are the same mineral? Yeah.
There are forming conditions?
Forming conditions, sure, but in a roundabout sort of way. Who likes Jell-O? It's all right. You know, I kind of like Jell-O. My kids eat a lot of Jell-O, so I have it around, right? Jell-O has the same consistency, often the same hardness, the same optical property, right? All Jell-Os pretty much look the same except for what? Color, which is often tied to taste, but that's irrelevant to minerals most of the time, okay? Let's talk about the color. The color of different Jell-Os, without tasting it, the only difference you'd be able to see between them is their color, right? And what dictates the color of Jell-O? The coloring they put in it. One ingredient. That's the only difference. It's true for quartz as well. They share the same chemical structure, SiO2. That's it. But guess what? Something else got stuck in there. In the case of amethyst, amethyst is purple. Why? Because there's a little bit of iron that got stuck in there between the SiO2s. Rose quartz is pink. Why? Because there's a little bit of potassium that got stuck in there between the SiO2s. Milky quartz is white. Why? Because a little bit of calcium got stuck in there between the SiO2s. You get the idea. We call these inclusions. And they can make the difference in colors in the different varieties of quartz. Okay? Then we've got muscovite mica. Muscovite mica has one plane of cleavage, so it splits apart into pages, like a book. Okay? You're looking at many different plates of them that have grown into each other, but each one of these plates will split apart, has cleavage in one direction, and so will separate into sheets like a book. Ladies, if any of you use makeup that has glitter, that glitter is made out of muscovite mica, more often than not. They crush it up and then use it for glitter and makeup. Then we've got clay. Clay is something that we will discuss a lot more later on when we discuss sedimentary rocks and weathering and erosion. It is what is referred to as a secondary mineral. Clay is often the result of the breakdown of light silicate minerals. Okay? But it's worth mentioning here because it is formed from mostly light silicate minerals later on. Okay? Clay is more or less the foundation, the bulk of what makes dirt, soils. Okay? Very fine-grained, weathered, broken down pieces of other minerals. How many of you like milkshakes? I love a good milkshake. You ever wondered how they get that interesting consistency? It's not frozen, but it's still really cold. It's not like liquid like water, but I can still suck it through a straw. How do they get that weird texture? They put a little bit of clay in it. there is just the tiniest bit of clay in your milkshake to give it that unique consistency because of the way that clays interact with water. Okay, it has a, it's very absorbent. Okay. All right, now let's talk about the dark silicates for a minute. That is the ones at the top of our scale here. Okay, starting with olivine. Come on now. All right. This is one of my favorite types of rock. This is called peridotite. I think it's beautiful. The greens and the black all mixed in together. Peridotite like this is what the mantle is mostly made out of. If I were to reach down 40 miles underground and pull out a handful of magma or rock, it would be magma when it came up because of the lower pressure. But once it cooled off, it would essentially have the same chemistry as this, right? This is peridotite. The green, that's all olivine. The little black ones in there, those are pyroxenes. Okay, pass this around. So olivine is the mineral that forms first at the highest temperatures, which is why so much of the mantle is made out of it. Okay, it's as hard as quartz. It's pretty hard. It's a 7 on the hardness scale, but it decays very quickly at the Earth's surface. It falls apart very easily up here. Why? Let's use some logic to figure this out together. Where is olivine form? Huh? High temperatures, deep underground. Why would it fall apart easily up here?
The difference of pressure?
Difference in pressure? Huh? The environment is different. So the pressure and what else is what's the other big factor? Temperature. Bingo. Pressure and temperature, vastly different up here than at its forming conditions. It formed where it was stable. It formed that deep under that much pressure and heat because that was a stable condition for it to exist in. Up here, it's not stable for olivine, so it falls apart relatively quickly. Okay? We don't see that crumbling to dust in front of my eyes. But that rock will fall apart a heck of a lot easier than most of the other things I've got here at my table because pretty much everything else up here formed up here in these conditions. Yeah?
What about selenite?
What about what? Selenite? Selenite is a type of gypsum and it's very soft. So it'll be physically and chemically broken down faster than pretty much anything else. Yeah. Okay. Pyroxene is the next one that forms. The little black crystals you see in there in that peridotite, those are the pyroxenes. Okay? It's very dark colored, usually black. Sometimes you can see it in like a brown, but it's usually a black. 2 directions of cleavage at 90 degrees. You'll be seeing some of that in the lab. Amphibole. Amphibole and pyroxene are often confused for each other. The easiest way to tell them apart from each other is their cleavage. Where pyroxene had 2 planes of cleavage at 90 degrees, amphibole has 2 planes of cleavage not at 90 degrees. And it'll be obvious. It's not a slight difference. It's like 60 and 120 degrees, right? It's very clearly not 90 degrees in amphibole, okay? And then we've got biotite, which is like muscovite, the stuff that you crush up and put in makeup, but it's a darker. This is the dark silicate version, the ferromagnesian version. It contains iron and magnesium where muscovite mica did not. Okay? It's the counterpart on the other side of the scale. And then we've got minerals like garnet. Garnet is what I kind of think of as a trash can rock. Or it makes trash can rocks. It is a mineral that makes trash can rocks, if I'm being specific. Okay? Garnets tend to form out of whatever's left over a lot of the time. So there are many different varieties of garnets that you can find. It's just kind of, whatever's left over after a certain process is complete. You'll find them in volcanic, in igneous, and in metamorphic rocks a lot of the time there. And they're also very hard. We use garnets for industrial purposes as well as jewelry. So you'll find necklaces out of the stuff, but you'll also find, abrasives for grinding concrete or metal made out of garnets as well. All right, now let's take a minute to talk about those non-silicates. I shoved them over here, and now I'm bringing them back. 92% of all of the minerals on Earth's surface are silicates, but the other 8%, non-silicates. Some of the ones that you might be most familiar with. Okay, let's talk about what makes, some of the most common non-silicate minerals. Halite. Hey, what was halite? You remember what I told you? Salt, yes. Halite is salt. Salt is a mineral. It is in the halide family. Okay, hematite, magnetite. Those are iron oxides. That's where we got a lot of our iron that we make metal stuff out of. It comes from those two minerals. Okay, corundum. You probably know corundum is a different name. Ruby, if it's red. Sapphire, if it's blue. But it's the same mineral, corundum. What does that say? Why is ice on this list? What's that doing there? That's got to be a mistake. Someone tell me what the definition of a mineral is again. Pull up those notes. I know you wrote it down. Whoever says it, say it loud so we can all hear it. Well, but there's the one definition that I wanted.
Naturally occurring or inorganic solid that possesses an orderly crystalline structure and can represented by a chemical formula.
Bingo. Any naturally occurring, stop me if ice stops ticking off these categories. Naturally occurring, inorganic, solid, that possesses an orderly crystalline structure and can be represented by a chemical formula. What's the chemical formula for water?
H2O.
H2O. My friends, ice is a mineral. Chills down the spine, right? That is why glaciers, thank you. That is why glaciers, the study of glaciers, falls under geologists, right? Glaciology isn't just the domain of climatologists, it's the domain of geologists too, which is why we have a whole lecture on glaciers coming up later in the semester, okay? Ice is a mineral. How cool is that? Cool, I did it again, not even trying. All right, so a whole bunch of the resources that we rely on actually comes from this list of non-silicates. Water, obviously, duh, right? Gypsum. We use gypsum to make drywall. Your houses have drywall in it, right? Gold, copper, diamond, sulfur, graphite, silver, platinum, all of these things, non-silicates, all vital to the continuation of our civilization, okay? Which takes us to a short discussion on mineral resources. There are a few terms that you should know when it comes to mineral resources, okay? Pretty much everything that you see around you comes from a mineral resource. My laptop, your phone, your glasses, this table, everything that you see around you comes down to a mineral resource at some point in its creation, okay? Which means that we kind of are reliant on the mining industry and, to an extent, the petroleum industry. Nobody wants to destroy parts of our world to get the things that we need. Unfortunately, the destructive practices are also the ones that tend to be the cheapest. There are many possible non-destructive mining operation opportunities. They just simply cost a heck of a lot more, at least right now with our current understanding of technology. So mining and petroleum drilling and all of that is still going to happen. And it's going to keep happening. And there are a lot of very passionate folks out there, perhaps some of you belong in this category, who are adamantly opposed to the continuation of those practices. But here's the truth, they're never going to stop. It doesn't matter who's president. It doesn't matter what Congress says. We're still going to be drilling for oil. We're still going to be mining metal, because that's the only way to keep the engine moving. Okay? We may mitigate effects, and we should. We may regulate destructive practices, and we should. But we're never going to stop. Because if we stop, we go back to the Stone Age in a few generations. Okay? So, when you hear the term ore, what that's actually talking about, like an iron ore or a gold ore, what that's talking about is it is a rock within which there contains a certain amount of that material that can be used for economic value. I worked at a gold mine in Nevada for a while as an exploration geologist. I was part of a team that found a heck of a lot of gold out there. It was really cool to be on that team, and I loved it. But we didn't find chunks of gold sitting around on the ground. You don't do that anymore. Long gone are those days. You can't just go find gold nuggets sitting around. Instead, what we found was ore, a deposit of rock within which there was a high enough concentration of gold that you could, by harvesting that rock, extract that gold and get an actual profit out of it. Now, at the time I was working at this mine, it was 0.03 parts per million. That is 0.03 parts per million of gold in any given rock. You would have to take 500 tons of rock to get 1 ounce of gold. And we did. And gold is high enough in value that the mine could make a profit out of that. Okay, so this is the way that the mining industry works. Nobody goes after a resource that they can't make money on. And that sounds super capitalistic, and it is, but it also makes sense because you can't run a business for free, right? You have to make profit or your business just doesn't work. Okay, so that's the way it goes. There's always the cost versus profit analysis that you got to be doing. This is the Bingham Canyon copper mine. Yes, it's an open pit mine, just like the gold mine I used to work at was, but this one's significantly bigger. For context, for scale, yes, those are mountains behind it. This is a very, very deep pit, right, that they've been digging in for a very long time, decades and decades, yeah. I couldn't even tell you how deep that is, but you can fit some of those mountains in there. Right? They've been hauling rock out of here for a while. Now, that cost versus profit analysis is extremely important. If the cost of extracting copper, like what the Bingham Canyon does, they extract copper. If the cost of copper is greater than the value of what they can sell it for, you shut down. So what happened here was decades ago, I want to say this was 80s, but I'm not certain actually. I should look up the actual date and put it on the slide. China started to flood the market with copper, which meant that the Bingham Canyon mine here in the United States faced two choices. Either we shut down because we can't keep up with the prices that China is selling copper for, or we revamp our entire system to make it more efficient and therefore reduce the price of our copper as well. And luckily for us, they invested about $100 million at the time, I think it was, to completely redo their whole system, which meant that they were able to compete with the Chinese copper. And this mine still operates today, okay, providing a very strong source of copper for us and a lot of other people, which is very good because what China likes to do is exactly that. They like to take over a market, force out all of the rest of the competition by buying them out or shutting them down, and then they just own the market. China loves that stuff. That's the game that they play. Okay? They've done that with something called rare earth elements. Have you ever heard that term, rare earth elements? They're down here, the lanthanide series. Okay? This lanthanide series of elements down there, rare earth elements. Every single piece of complex electronics that you have, your phone, laptop, Xbox, night vision goggles, Tomahawk missiles for the military, every single one of those requires one or more rare earth elements in the computer. And China owns 98% of the market on them because they forced out every other competitor. Anytime anyone else wants to start a mine for rare earth elements, they drop the price. So all of a sudden, nobody can afford to start that mine because they wouldn't make a profit. And then they just hike the price back up once that operation is done. Kind of got everyone by the family jewels on that one, right? All you have to do is piss off China enough, and they say, you know what? I don't think you'll get any more rare earth elements. And then they can't manufacture their own electronics. They rely on everyone else to sell it to them, which puts them in debt to a whole bunch of other people. Yeah?
How do you think China dealt with the tariffs?
How do I think China dealt with the tariffs? I think they mostly just laughed. Yeah. They experienced some hardship for sure. It's a tricky conversation to have because I have views on China ideologically. I have views on the government of China and the people of China in totally different viewpoints. Love the people of China. I've known so many people from China. I adore them, right? The government of China I have strong issues with. The way that they treat their people mostly, right? And I'm not going to make any political commentary on that. But the ways that they do business, especially when it comes to mineral resources, it's dirty, man. So I think that a certain amount of tariffs on goods are probably justified by any country. Heaven knows that there are plenty of other countries that do it. I do think that our own government may have stepped over the line a little bit hard when it came to blanket tariffing everybody. But I think that China can most certainly afford to pay tariffs, right? However much those tariffs are, I'm not informed enough on our trade negotiations with them to say what a fair tariff for China would be. But I think that they could probably do one and be fine. Yeah. But yeah, I mean, that's kind of, yeah, sorry. You may, yes. That's kind of a big part of the reason why people are so afraid to piss off China is because so many people are reliant on them for their resources. And China knows that, which is why they have absolutely no qualms about forcing billions of people to work for practically nothing to get those resources. Okay. Yeah, so that's kind of where an insight into the mining and resources world that you may or may not have known before. Any questions about anything we've talked about today? No? Did you learn something today? Was it interesting at least? I hope so. All right. So let's move into lab time now. We've got about 40 minutes left in class. So you've got your kits in front of you. I'm going to hand out the trays of samples here in just a minute. Let me close this. And, oh, it's zoomed in on me. Zoom out. Zoom out. Zoom out. There we go. And follow. Good. Okay. Now let's go back to let's go to our labs, and I'll open up the lab PowerPoint, which you do have on Blackboard, by the way. All of these resources I show you, these are on Blackboard. Okay, so there are two very important things that you're going to need to use for this lab. Okay, you're going to need this PowerPoint. It goes over everything I just went over about the lab, just in more detail, right? Oh, have you guys ever seen Journey to the Center of the Earth with Brendan Fraser? Yeah? Okay, this is my favorite part of the movie. So just a little context, our heroes have just entered a volcanic tube, okay, deep underground, and they're going through, and they find that this tube has lots of different minerals inside of it, okay? Let me make sure that the sound is on, actually. Okay. So Brendan Fraser plays the geologist, by the way. The other two people that are with him, one is his son, and the other one is their cave guide, but is not a geologist.
Feldspar.
You get the joke. They're like, look at all of these gemstones, and he's looking at the feldspar. Like half of our crust is made out of feldspar. It's funny because that's something a geologist would absolutely do. That's something I've done many times. So it's funny, I guess, if you like irony. Okay, so this is just going over all of the same stuff we talked about today, just in a little bit more detail. It has the list of things like your crystal forms and all of that. On this slide, slide 5, that is a link to a website that has interactive, rotating 3D models of all of the possible crystal forms that you could see for the lab. Use that resource. Sometimes the school blocks it here. I don't know. They change their firewalls all the time here. This website is hosted in the Netherlands. You see that .nl? That means that it's in a Netherlands domain. It's not a .com, so it's not a United States domain. So sometimes the school blocks it. If it is, you'll need to open that website when you get home later. But that's just something for you to use there. It goes over the cleavage, just some reminders and examples, how you tell hardness, color, streak, luster. That shows you the different types of luster as we learned about it. All of that stuff, tenacity. It just goes through everything we just talked about, right? So now let me show you or tell you about your other resource. In the Lab 1 folder, there is a spreadsheet, an Excel spreadsheet that says, you will need to use this. It says that for a reason. That Excel spreadsheet is your database. Okay? It is your Rosetta Stone for labs 1 through 4. Okay? You're going to use that in every single one of those labs because it has all of the possible minerals and rocks that you could be looking at for every single lab. It has all of the properties for samples 1 through 51 on your Lab 1 practice set. So, as you're going through the 24 on Lab 1, you're going to be finding these properties, observing them for yourself, recording them, writing them down. Then, as you complete your list of properties that you observe, you're going to go to that spreadsheet and you're going to start process of elimination. I'm looking for something that has cleavage at 2 angles or at 2 planes at 90 degrees. Eliminate everything that doesn't have that from that list. I mean, don't delete it. You don't want to do that because you want to reuse it, right? But you can look only for things that have those properties. Then, out of all of the things that have 2 planes of cleavage at 90 degrees, I'm looking for something that is also has a hardness greater than 5.5. Eliminate everything that doesn't have those 2 properties in common. And through this process of elimination, you are going to find, hopefully, the right sample name for your mineral that you're looking at. And by the way, this is the exact same process you're going to be doing for labs 2, 3, and 4 as well, just with rocks instead of minerals. Okay? So you have 24 samples in Lab 1. Work as a group. However, do not let one person do all the work. It will not do you any favors. Because guess what? There is a lab exam over this stuff later in the semester. And if you've let someone else do all the work, guess how well you're going to do on that exam? Not very well, right? Don't let that be you. Share the load, share the work. Help each other understand why the answers are the way that they are. And here's another little thing. Exams, I mentioned this before, exams are the only assignment in my class you cannot redo. You can do this lab and every other lab as many times as you want to get the grade you want or to understand the content the right way. Okay? It's just dependent on how much time you put into it. Sound good? Any questions before I hand out the lab samples? No? I'll hand them out, and then you can just leave them on the tables, and we'll just come back next week, and you can keep working on the lab then. I give you a little bit of extra time on Lab 1 because it's your first lab, but also it's twice as long as the others. All of the other labs only have 12 samples. This one has 24 because these are the minerals that make the rocks that we see later, and you need a firm grasp of the foundation of the concept before you can get everything else better. Okay? All right, I'm going to end the recording here and hand out the samples for my online students. You have your Lab 1 exercise set video. That is what you are going to be looking at for this lab to identify.